Okay, so in the last video on the 383 here, Dad, aka the cleaning guy, went through and reground the crankshaft to get us within the tolerance that we wanted and set our main bearing and rod bearing clearances according to what we measured here on the block and on the rods. I've actually gone through and done some of the assembly leading up to that, but today I want to take you through some of that as well as degree the cam here and kind of talk about some of the verifications that we do while we're assembling an engine like this. Before going ahead and installing the piston rings on the pistons and getting the short block assembled here, I actually wanted to do one more clearance check. Since this is a stroker kit, we do have a rotating assembly that we needed to double check clearances on the block, clearance with the camshaft, clearance on basically everything. So I went through and lubed up the camshaft and got it installed, and then I went ahead and installed the crankshaft. I'm gonna get bearings lubed up. Hopefully I don't have to take the crank back out, but we will if we have to. I'll have to do a bunch of cleaning on it.
Whoa, 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 what are you doing?
What do you mean?
You can't use ketchup on a race motor.
What else am I gonna use?
You need to use this. It's a little more spicy.
Arouses and releases?
Yeah, it releases the horsepower.
Okay.
Use it. Trust me, it'll work.
Now, before actually torquing down the main caps, we did bump the crank back and forth a few times, ending with bumping it forwards to align the thrust on the rear main there. After we got everything torqued down, our crankshaft end play is sitting at about 3/1000ths of an inch, which is on the tight side of the tolerance. We have an adjustable timing set that I currently have installed straight up, meaning that there is no advance or retard on the camshaft right now. So at that point, I went ahead and put a little bit of assembly lubricant on the bores of the piston as well as the pin bore of the connecting rod and installed the pins, making sure that the connecting rods and pistons are all oriented correctly for their corresponding cylinder. These pistons do use spiral locks for the retainers, which I know is everybody's favorite because who doesn't love having bloody fingers after you're done getting the pistons installed on the connecting rods? So again, without having the piston rings installed, I installed all of the pistons one by one and just double checked that we did have clearance everywhere with the rotating assembly, including between the camshaft and the rods, as well as the block itself. Everything checked out good, so we went ahead and moved on forward with the assembly. We do have file to fit piston rings, and I went with a combination of the manufacturer's recommendations as well as just some baseline experience on this type of application for our ring end gap. And we came up with 4.5 thousandths on the top ring per inch of bore and 5 thousandths per inch of bore on the second compression ring. And doing the math, that puts us at 18 thousandths gap on our top ring and 20 thousandths gap on our second ring. To go through and check that, we simply use a ring squaring tool to square the ring in the bore, and then we use a feeler gauge set to check and see where the gap currently is. These being file to fit rings, they were super tight to begin with, so we did end up using our Total Seal piston ring filer to file the piston rings for the correct gap. The machine is adjusted to hold the piston ring such that you're filing material off nice and square, and then we can reference the dial indicator to remove the required amount of material. The machine also has a deburring wheel to take off any sharp edges that are left behind when you're done, at which point you can recheck the gap and repeat the process as necessary. One thing to note is that you do want the gap to be nice and square, as you can see here, so if it's coming out a little bit cockeyed, then you can adjust the machine accordingly. I did also check the oil scraper rings, but they had plenty of gap out of the box, so we didn't have to do any more filing there. After gapping the rings, I went ahead and got them installed on all of the pistons, making sure that the top ring and the second ring were in the correct grooves and oriented correctly. And then I did go ahead and align the gaps in the piston rings according to the recommendations from the manufacturer. And at that point, I was ready to go ahead and get the pistons all installed in the block. Sometimes you'll actually see guys completely dipping the piston with the rings on in a bucket of oil before assembling them in the block. And we just don't feel that it's necessary to do that. It just fills all of the grooves with oil that gets cooked right when you start up the engine. What we actually do instead is we simply take some assembly lubricant and line the cylinder with it and make sure that it is lubed up really well, but then just simply install the piston after that, and that gives you enough lubrication for startup. So I did go through and install all 8 piston assemblies in their corresponding cylinders, making sure that all of the pistons are oriented correctly, again, kind of like I mentioned earlier. At that point, I torqued all of the rod bolts to the specifications set by SCAT, who is the manufacturer of the connecting rods. On the bottom end here, the rod side clearance looks to be pretty good, and I'd say that pretty much brings us about to where we are right now, getting ready to degree the camshaft. Cold turkey may be great on sandwiches, but there's a better way to break your bad habits. No, I'm not talking about all the tricks buried in that self-help book that your wife bought you last Christmas. We're actually talking about our sponsor for this video, Fume, and they look at the problem in a different way. Not everything in a bad habit is wrong, so instead of a drastic, uncomfortable change, why not just remove the bad from your habit? Fume is an innovative, award-winning device that does just that. Instead of electronics, Fume is completely natural. Instead of vapor, Fume uses flavored air. And instead of harmful chemicals, Fume uses all natural, delicious flavors. So I'm sure by now you get it. Instead of bad, Fume is good. It's a habit that you're free to enjoy and makes replacing your bad habit easy. Your Fume comes with an adjustable airflow dial and movable parts and magnets for fidgeting, giving your fingers a lot to do, which is helpful for de-stressing and anxiety when you're breaking your habit. Fume has plenty of cores to choose from to match your flavor preferences, like raspberry lemon, the sweet and citrusy orange vanilla, or my personal favorite, crisp mint. I love the clever yet simple design of the device, and I was surprised at how fresh and natural the flavors were. Stopping is something that we all put off because it's hard, but switching to Fume is easy, enjoyable, and even fun. Fume has served over 100,000 customers, and there's thousands of success stories, and there's no reason that can't be you. So join Fume in accelerating humanity's breakup from destructive habits by picking up the Journey Pack today. Head to tryfume.com/jams or scan the QR code and use the code JAMS to get 10% off when you get the Journey Pack today. That's tryfum.com and use code JAMS to save an additional 10% off your order today. Thank you again to Fume for sponsoring this video. So I'll actually go through here and talk about a couple different ways to degree a camshaft. They kind of all end up with the same result, and different people like to do it a different way, and on a different cam it may make sense to do it one way or the other. Right now I do have, like I said, we have the camshaft installed, we have the timing set installed straight up with no advance or retard. We are actually using link bar lifters when we go through with the final assembly, but I've just got some normal lifters in here, the non-link bar type. They are still roller lifters, but just factory roller lifters, and I've got the dog bone in there to keep them straight. And I also have these little, almost like a diamond here, that kind of gives a flat surface for the indicator to ride up and down on as we do this. You can degree the camshaft with the head installed, but I personally like to do it with the head off if I have the ability to. So it's kind of hard to get the camera set up to where you have all the action going on here, but I set it up here so that you can see at least the pointer that I use, which, yes, is a coat hanger. I've got this big Moroso Pro Wheel degree wheel. What I usually do, at least to start with, is run up the piston to where, just eyeballing it, it is at top dead center. But you don't want to just use the pointer here at that point because you may not actually have true top dead center. A couple of different ways to do this. You can have a dial indicator on here like I have, and I've basically zeroed the indicator at the highest point. And then you can go backwards 50 thousandths and then past top dead center 50 thousandths and read your reading here on the degree wheel and make sure that they read the same number, or adjust the pointer here if you need to. I personally like to use a positive stop instead, so I'm just going to roll this backwards enough here. And you can see I've got this deck bridge actually bolted down here. I'm just going to slowly run turn the crank around until that hits, and you'll feel it stop. That's why they call it a positive stop. So right there, I've pushed the piston up against the deck bridge here, and just getting a straight on reading here. You might have a little bit of parallax in the camera there, but I'm reading a reading of just over 12 degrees here on the wheel. So now we're going to rotate backwards all the way around. And right there I bumped again. And I'm just a little bit off, but I can just kind of tap that over. And again, we have a reading of 12 there. We have a reading of 12 on the other side. That means that when our piston is actually at 0 degrees here on the degree wheel, it'll be at top dead center. Just for fun, I'll do it with 50 thousandths there on our indicator. It doesn't have to be 50 thousandths. It's as long as you go to the same reading both times. So right there, we have a reading of 50 thousandths on the indicator And I'm going to call this about 11.5 here on the degree wheel. Now we'll go right up past 0, and on the way back down, there we are again. And again, on my degree wheel here, I'm reading 11.5, which again shows that when we're reading 0 on our degree wheel here, we're going to be reading true top dead center of the piston. That's the first thing you have to do. No matter how you're going to degree the camshaft, you have to get your degree wheel aligned at top dead center, true top dead center on the piston, number 1 cylinder. This is the cam card that came with the camshaft from CompCams, part number 08432-8. So this cam has 510 intake lift, 520 exhaust valve lift with 1.5 rocker arm ratio. Sometimes it'll say right here, these specs are for cam installed at, say, 106 intake center line. For whatever reason, this cam card doesn't list it. We can still find what the intake center line is supposed to be by taking these numbers here, which it actually says is valve timing at 50 thousandths lift, which these are not the events at 50 thousandths. These are the events at 6 thousandths lift. Regardless, we can find the intake center line, 35 plus 67 plus 180 divided by 2 minus 35 gives us 106 degrees for our intake center line. Now, personally, I don't really like that cam card, so I have a spreadsheet that I plug them into, and I make my own cam card that shows these are the valve events at 50 thousandths lift. And this is only going to work on a camshaft with symmetrical lobes. There are camshafts that have asymmetrical lobes, meaning the ramp on the opening side of the valve and the ramp on the closing side of the valve do not follow a symmetrical profile. So what I've done is gone through, and again, we have a 106 intake center line. That means that the intake should be open 50 thousandths at 9 degrees before top dead center. It should be closing 50 thousandths at 41 degrees after bottom dead center. And correspondingly, these are the numbers for the exhaust lobe. But we're going to start with the intake side. So again, we've got our degree wheel set up and aligned for true top dead center. And I've also got a dial indicator here on the intake lifter there for number 1 cylinder. So we're going to start with that. So as per the instructions from CompCams that came with this camshaft, the method that they tell you to use is the intake center line method, but they tell you to make your references off of the 50 thousandths points on either side of max lift. So what they tell you to do is, after you have your degree wheel set up there on true top dead center like we did, they tell you to rotate this around until you find the max lift point of that intake lobe, which I'm going to say is about right there, and then 0 your dial indicator. Because you might be tempted to try and just run that indicator to where it's, at the max lift point, and then say, oh, it looks like it's about, somewhere in between 100 and 110 degrees, but it's not accurate enough to do it that way. So what you actually have to do, we're going to back off about 100 thousandths here. And now, as we come up, we're going to stop at the 50 thousandths mark from max lift. I am right on 50 thousandths lift on this dial indicator over here, and we have a reading of just over 62 degrees. So let's call it 62.25. So now we'll rotate on to max lift and go back, and as we come down, we're going to stop at the 50 thousandths mark again, and right there we have 50 thousandths lift, well, 50 thousandths from maximum lift of that lobe on the opposite side, on the closing side, and I'm going to call this 152.25-ish. You take your 62.25 from the opening side, and you add 152.25 from the closing side, and we have 214.5 divided by 2 gives us an intake center line of 107.25. So that's telling us that based on that method, when we know our intake center line is supposed to be 106 according to the specs of the camshaft, our cam right now is a little over 1 degree retarded. Now, I kind of think, I don't know which way is most accurate, because It seems like people have different opinions and different manufacturers tell you to do it one way or the other. I don't know, maybe that's the most accurate way, or maybe they just do it that way because it requires the least amount of math. But I kind of like to go off of the valve events at 50 thousandths lift, which, you know, if they're not telling you them, is kind of complicated because you have to use the duration and the center line to find exactly what those numbers are. But let's go through and check it that way. I'm going to rotate all the way back until we're on the base circle of the cam, and I'm going to zero that indicator on the base circle. And now, as we come up, let's keep going on around to 50 thousandths. Okay, so at 50 thousandths right now, we're reading probably 6 3/4, I'll call it. We're supposed to be 9, so we're a little bit over 2 degrees retarded based on the opening point there. And we'll go around past max lift. And as we come down, we'll stop at the 50 thousandths mark, and we're probably 42.5. So I added 42.5 to 6 3/4 plus 180, because we're halfway around, gives us 229.25. The duration at 50 thousandths on this cam by the book is 230, so we're fairly close there. We're within 1 degree. Now I'll divide that by 2, subtract 6 3/4, and it tells us we have an intake center line of 107.87. Again, we're supposed to be 106. So we're closer to 2 thousandths retarded than 1 thousandths retarded. So again, a little bit of variation, but at the end of the day, we're retarded by at least 1, if not closer to 2 degrees. I think I was saying thousandths there, but I meant degrees. And again, I think we had gotten 42.5 on that closing point, and by the book, or by the specs, it would be 41. So again, 1.5 degrees roughly retarded on this camshaft. So most everywhere you look, they're gonna tell you to just go off the intake lobe on #1 cylinder. But I'm gonna set up and do the exhaust lobe just for fun, just to double check. So again, the center line on the exhaust lobe should be 114 by the specs of the cam. We'll just go off the 50 thousandths opening points. All right, 50 open by the numbers should be 52 before bottom dead center, and we are just over 50. So again, that puts us close to 2 retarded. And we'll come on around to our closing point, and there were 50 thousandths from the closed, and we're a little over 5, and by the book, we should be 4. Will put us at 112 3/8, which again puts us about less than 2 thousandths from where we're supposed to be. But we are retarded a little bit. Okay, so we checked a couple different methods here. We checked the intake lobe and we checked the exhaust lobe just for fun. Most people are just gonna check the intake lobe on #1 cylinder here. And we found that we are over 1 degree retarded on our cam timing right now. So what do you do at this point? Well, 1 degree, you could just leave it be. But our opinion, we would rather be slightly advanced over slightly retarded. Couple reasons. One, advancing the cam a little bit is going to give us a little bit more low-end power for the customer. And the #2 thing is, over time, as the components wear, the camshaft is gradually going to become more retarded. So we'd rather start with it advanced as opposed to starting with it already on the retarded side. So now I have to take our timing set back off, and we'll change the crank sprocket here. Well, not change it, but move it. Pop our timing set off. I don't know if I mentioned earlier in this video, but the timing set has a little Torrington bearing here, and we're using the factory provisions for cam plate, so we don't have to mess with a cam button like you would on a retro roller cam. So as you can see, the crank sprocket here has multiple different keyways. I think there's actually, what, 9 different keyways around here that allow us to go in 2 degree increments there to either advance or retard the camshaft. What we're actually gonna do is just go to this 2 degree advance keyway here, just the next adjustment that we can make so that it's not excessive, and basically get the gear reinstalled there and reset up our timing set and check again and see if we're in a good spot. Okay, so now that we have the A2 keyway on here, I need to line up with, instead of lining up our timing marks with just the dot here on the crank gear, I'm going to line it up with the A2 on the crank gear. So you can see we're on the A2 keyway. I have the A2 mark on the crank sprocket lined up with the timing mark on the cam sprocket. We've had people who thought that you still had to line it up on the dot, and they're in the, they're in an advanced or retarded keyway, but they're still lining it up on that normal straight up tooth here, and that'll give you trouble. So you got to line it up correctly. Timing set is now advanced 2 degrees. I went back through, got the degree wheel set back up with it on true top dead center, yada, yada, yada. Let's go around and we'll do it. We'll do 50 thousandths from max lift first. So there was our 0. I have a reading of 60.5 degrees. Now we'll go past max lift. Okay, 50 on the way down. We have a reading of 150.5. So let's do some math here. 150.5 plus 60.5 divided by 2 gives us a center line of 105.5. Again, by the spec, it's supposed to be 106. So now we are a ½ degree advanced, which is, right where we want to be. Let's check it with the other method where we're 50 thousandths tappet lift and see what that comes out to. And again, drop your comments. Let me know which one you think is more accurate. I generally use the 50 thousandths tappet lift, but I've been wrong about things before. It's on 0. Again, now we're looking at the timing events at 50 thousandths lift. There we have 50 thousandths lift, and man, we are right on the money at 9 degrees. And if you remember from our specs, we want to have our intake open 50 thousandths at 9 degrees before top dead center. That's right where we are on the open point. And I'm going to call that 140 and a half, if not 140 and 3/4. And again, sorry, not 40, not 140, but 40 and a half or 40 and 3/4 after bottom dead center, which is over here to the right. We were looking for 41, so we're within no more than a ½ degree off. And again, let's do some math. We'll call it 40 and a half plus 9 plus 180, since we're halfway around, divided by 2 minus 9, 105.75. So, within a quarter of a degree from what we measure using the other method. And again, our intake center line is supposed to be 106. We're at 105 and a half one method, 105 and 3/4 the other method. So we're exactly where we'd like to be. So when it's all said and done, looking at all of the opening events on the intake and the exhaust, and as well as looking at the center line of the intake and the center line of the exhaust, we're coming out probably about a ½ degree advanced, which we feel is a better place to be. All right, it's a new day, so we're getting back into it here on the 383, going through some of the assembly and some of the checks that we're doing. As you saw, probably, or maybe I'll put that in right now, our pistons came out slightly lower in the hole than we were expecting. I think we ranged between 6 or 7 in the hole to close to 10 or maybe 11 thousandths in the hole, which is kind of disappointing considering all the work we went to on getting the crankshaft straightened out and decking the block and so on. They're kind of all over the place, so I'm assuming partially it's in the connecting rods, but that's what tolerance stack up does. You have different tolerances on each one of those parts, and sometimes they stack up differently. So with that being said, since we are a little bit deeper in the hole, originally we were going to run a 40 thousandths thick head gasket. I actually went ahead and ordered 36 thousandths head gaskets, so we just got a little bit closer to get us kind of back where we wanted to be as far as our quench and so on. With that being said, I don't want to waste a gasket when I'm doing our piston valve checks here and setting up our rocker geometry. So I actually used the Wazer water jet and I cut these out. There will be a short video, one of my YouTube shorts on that. I ordered this, it was supposed to be 40 thousandths thick. It ended up being 34 thousandths thick. So it's actually pretty close to our final head gasket dimension compressed thickness. So basically what that's gonna do is we can drop these on the deck here. And now when we put the head on, it's basically shimming everything to simulate our compressed thickness there. And again, it's 2 thousandths off, but 2 thousandths isn't really gonna make a difference. So got one of our heads out. I'll still be planning on doing a video of kind of going through and checking the heads a little bit more, but just haven't gotten around to it yet. But I'm confident that they're gonna be at least within reason to where we can check our piston valve clearance and kind of set up our rocker arm geometry, because I checked them enough to see that I think the valve job is actually pretty nice on these, which I would hope so because these are a pretty expensive set of heads. And I've got some checking springs on here so that makes things easy. I am using our normal hydraulic retrofit lifters in here, our roller lifters. With that said, these checking springs are light enough that the lifter doesn't bleed down. If you have thicker springs on here when you're doing these types of checks, you need to have a solid lifter in. I'm actually gonna put some head bolts in, kind of show you guys. Here we've got a 35 thousandths feeler gauge, and it almost, if you wiggle it just right, would go in. If I forced it, I think it would, but I don't want to mess up the deck or the surface of the head. That's to give you kind of an idea that we are close to our 36 thousandths compressed head gasket thickness for these checks. We are going to need a dial indicator mounted on the head for these checks. Just give it a little snug. And that allows us to articulate and get over here on the retainers for each valve and so on. So I'll just kind of lock that there for now. I think we'll start with figuring out our rocker arm geometry here on the exhaust and intake. Theoretically, they'll be pretty close to the same because our lift is relatively close to the same on both the exhaust and the intake. Our valve tip heights are the same, and everything else is basically pretty close. I mentioned that the way that I typically do things is with the mid-lift method. Typically, you're going to read that they want you to get the sweep centered on the valve and as narrow as possible. A lot of times, people are basically just making adjustments and looking at the sweep on the valve, and that's a fine way to do it. That's an easier way to do it, probably. It's maybe just not quite as accurate as doing it with the mid-lift method, but that being said, I'd like to see you guys' comments of what you think of the method that I use, as well as if you think there's something easier, because like I said, this is just the way that I typically do it, but that doesn't mean there's not something better out there. With the mid-lift method, the goal is that when this valve is open to mid-lift, meaning halfway to the maximum lift point on your valve lift, if you drew a line parallel with the valve stem, and then you drew a line from the center point of the trunnion here that the rocker pivots on, and the center line of the roller on the tip, at mid-lift, you would want those two lines to be perpendicular. There's actually a good video on YouTube from Straub Technologies on how to go about doing this, but we're gonna run through it really quick here. So we'll put the adjustable push rod in. Again, I do have a hydraulic lifter in here right now, but my checking springs are so light that the spring isn't strong enough to bleed down the lifter. Drop our rocker into place. We'll start by putting our nut just barely on the stud there. So we're just holding it up against that adjuster nut, not strong enough to push down the valve, but just, so that there's no slack in the system. And what we'll do is start adjusting this nut down. See, obviously, if I went that far, you can see that we definitely don't have a 90-degree angle here. Try to get the camera lined up with, obviously that's way too far, so I'm gonna back this back off. I'm actually going to adjust the camera down, and I'll show you guys with my other camera. I have my tripod set up, and on my cell phone here that I'm recording with, I have the grid lines set up. They give you an idea of if you're taking a photo that's square to the world, basically. And what I've done is that vertical line there, I'm attempting to get it as close to parallel with that valve as possible. And then we can use that kind of as a reference, the horizontal line, to make sure that we're adjusting to be perfectly 90 degrees. So with that said, let's see, I might just adjust a tiny bit lower. Probably about like that is going to put us pretty well centered there. Okay, so at that point we've got everything square like we said. You know, that center line running through the two trunnions to the center line of the valve are both perpendicular to each other, but you're like, what the heck, you're not even open at this point, so why is it called the mid-lift method? Well, at this point, we have to run the adjuster nut here down to the point where we would be at half lift. The thread on our studs here is 3/8 24, meaning 24 threads per inch. You take an inch, divide it by 24. That tells you that each revolution of this nut is going to lower the center point of this trunnion by 42 thousandths. We're on the exhaust valve right now. So by the book, our exhaust cam lobe lift is 347 thousandths. These are 1.52 rockers. So our lift is 527 thousandths. We'll divide that by 2 to get mid-lift, and then we need to divide that by 42 thousandths to tell us we actually need to rotate this about just slightly less than 6 1/3 turns. So now, based on where that adjuster nut is, again, we need to go 6 1/3 turns. 1/3 would basically be 2 flats. So I'm going to start with our 1/3. Yeah, we'll go about like that. Would probably be just slightly less than 1/3. If you can't tell, I've got a little red mark there. So now we need to go 6 more turns. 1, 2, 3, 4, 5, 6. So now we've lowered our center point here to that, basically where it would be at half lift. So if we run this down to where it's about, 90 degrees or whatever, that's where half lift is going to be. This might be a little confusing if it's the first time you've seen it, but like I said, there's another good video on YouTube if you go search rocker arm geometry. Now we're going to adjust our push rod. So I mentioned we have an adjustable push rod in here. What we're going to do here is just adjust that push rod up. And again, I don't want to overdo anything because I don't want my lifter to start compressing on me. But right there, the rocker arm is pushed up so that basically there's 0 lash here. It's right at 0. Go ahead and take our adjuster nut off. Oops. Drop it in the engine, and we'll pull the push rod out. And this push rod has lines on it. Each revolution here is 50 thousandths of an inch. Typically, your off-the-shelf push rods are going to come in 50 thousandths increments, and that's what the comp push rods that we're using are, in 50 thousandths increments. This one is a 6.8 to start with, so now I'm going to count the revolutions that it takes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, so we've got 16 revolutions right there. 16 revolutions at 50 thousandths each plus 6.8 tells us that a 7.6 push rod is going to be the right length here. So I ran that push rod out, that 16 turns that we got to get us to our 7.8 length, or 7.6 length, excuse me. And let's go ahead and check the pattern while we're at it here. Oh, I definitely did not mention that you have to be on the base circle of the cam when you start. If you're not, it's going to throw you off. So, okay, I'm going to take the nut and I'm going to adjust to 0 lash. Being careful not to change my push rod any. So we're at 0 there. And again, I'm just adjusting this down until we have 0 lash. Again, if you've got strong springs, you're not going to be able to do this with a hydraulic lifter. Right there, I can feel 0. If I push, you can see the lifter starts, or the valve starts opening actually. So we're going to go right there at 0. And now we'll just rotate through a couple rotations here. Actually, first we'll go to mid-lift and look at it. 2, 64-ish. And just eyeballing it, we look to be in a pretty good spot. Let me bring the camera down. I'd say we look pretty square there between our 2 center lines that we would have drawn. So let's keep going. Theoretically, we're not going to have a lot of sweep, which is what we want. in our opinion. Some people have different schools of thoughts. You can see we're slightly that direction, but that's a pretty small sweep there. It's not perfectly on center, but in our opinion, having less sweep is more important than being on center, within reason. But again, like I said, let me know you guys' thoughts. It's not set in stone, but this is the way that I do it. We're repeating the process on the intake side, just accounting for the lift of the intake valve as opposed to the lift for the exhaust valve. I don't think is going to make very much difference. Pull our push rod. So we're slightly less 16. So the same number, which would be a 7.6. Okay, so last thing that I'm going to check here is piston and valve clearance on the exhaust valve and the intake valve using a dial indicator. So most of you guys are probably familiar with the clay method. I'll use clay here in a second, but I'm going to start with using the dial indicator. And a lot of people think that if you run the piston to top dead center, that's going to be where the tightest clearance is, but it's actually not true. Where you want to be is around 10 degrees before top dead center on the exhaust stroke. And that's where you want to check on the exhaust side. Because what's happening is as the exhaust valve is still closing, the piston is chasing it back up. And there's a point there where, you know, the relative speeds of each other, they've come together as much as they're ever going to peak. And usually it's around 10 degrees before top dead center. We'll start at 15 just for fun and see. So I'll set that at 0. 1. There we've got about 152. Around 12 before top dead center, we've got 145. And this is where it's probably going to be about the tightest. 142. Just went about 2 degrees more, so we're at 8. It's about the same. 5 before top dead center, and we're going back up. So we're 148 there, and let's just go to top dead center for fun. 165. So our tightest there was about 142 thousandths, which is fine. So now we're set up on the intake side. So again, just to show you guys, you know, our intake valve here has started opening. Let's just check where we're at, 20 before top dead center. Miles and miles. 10, because on the intake stroke you check about 10 degrees after top dead center. So now I'm at 10 before, which we should have plenty, and we do. Go to 0, 1, 2, well, 185. Let's go to 5. You have to re-zero the indicator every time. 165. Go to 8. 160. Now we're at 10, which is where it should be about the tightest. 160. 159. Let's go to 12. Because at this point, the piston is going back down, but the intake valve is also opening and starting to, accelerate open. So it's kind of chasing the piston back down the hole. So now we're 162, so we're going back up, kind of. We'll just go to 15 for fun. So at that point, we're close to 180. So the piston is really starting to speed up relative to the valve. It's always a good idea to still check with clay, and obviously a lot of people only check with clay, but using a dial indicator gets you a little bit more accurate of a reading of how much clearance you have, but it doesn't tell you how much radial clearance you have to the valve reliefs. So we're going to put some clay in and make sure that we have enough radial clearance. Clear back here is where the valve actually was. And this is the top of the head where it was squishing down. But definitely plenty of clearance on the exhaust side. Plenty of clearance there as well. All right, so that's a little rundown on the 383 here. I think it's starting to come together and feeling pretty good about it. You know, we ran through some of the assembly here on the short block and degreeing the cam, and then some of the setting up the rocker arm geometry. So I got to order push rods here. Hopefully they'll be here next week when I get back, because I'm headed out for the rest of the week to go to Texas with my wife to see the father-in-law. What else did we do? Check piston and valve clearance. Everything looks to be pretty good there, but I'm feeling pretty good about it. So I'm saying this kind of as a joke, but kind of serious. I don't do these videos completely for you guys. I also do them to learn. So if you guys see something that you think I did that's crazy wrong, be sure to call it out, because I actually do learn from the comments. I take a lot of them with a grain of salt, but every once in a while we get a comment that makes us think and actually makes sense. So I know you guys are out there, and I know there's a lot of you who watch our videos who know what you're doing. So give us your feedback, but in the meantime, I hope you enjoyed the video, and we'll see you in the next one.